ahead and have our last talk of the morning then by Hayato Takahashi, who'll be speaking about algorithmic randomness and stochastic selection functions.
I'm Hayato Takahashi from Japan. Today I want to talk about subsequence of random numbers. So, in particular, I want to talk about the algorithmic analogy for classical theorem on normal numbers. One of them is Steinhaus theorem. That Steinhaus theorem says that the sequence is normal number is equivalent to the random selection of almost all random selection of subsequence again normal numbers. In this talk, I also give algorithmic analogy for Kamai and Wise theorem. Kamai and Wise theorem says that selection, the necessary and sufficient condition for selection function that preserves all normality. Roughly speaking, Kamai and Wise theorem says that the selection function always condition for selection function preserve normality means the the entropy is zero. For example,
so can you explain what is x divided by
okay. Okay. So the meaning of x divided by means that the x is a binary sequence and y is also binary sequence. Then the selected sequence by y means that the subsequence selected by bits of 1. That is, if in this case, if x is like this sequence and y is like this sequence, then selected sequence is we select the bit is 1, that is, in this case 001 is.
Yeah, that's clear, but can you then show again the statement?
Statement, okay. Okay.
So what is then
this is this is IRD process with parameter is q. Q is, for example, q is 0.5, then this is uniform process. So this means that so
we say that if x is normal, then and we select each bit with probability q.
Yes.
Then
so
almost all.
Yeah.
Everywhere.
Yeah. So this means that x is normal, then almost every random selection again normal with respect to any parameter. The converse also true. So from almost every, if random selection is almost always again preserves normality, then original sequence is normal. So in this talk, I give some algorithmic randomness analogy for these two type of classical theorems.
Okay, sorry. Oh, okay, I didn't see the white, so the Yuki is on the white.
So
okay, thank you, sorry.
X and Y is always either 0 or 1?
Yes, X and Y always are binary sequence. I will explain later.
It's x where y
this is non-trivial notation. I will explain later. Roughly speaking, this is a very similar notion of entropy, but I will define later. But so in Van Ramberg's PhD thesis, he tried to show some algorithmic analogies to these theorems. In particular, he showed algorithmic analogy for this direction, and he also conjectured some algorithmic analogy for these theorems. In this talk, I will give some different result to different algorithmic analogies to these theorems. So the Van Barjan's analogies means that if he shows that if here RU is a uniform measure and RU means a multi-referendum sequence with respect to uniform measure, and this means with computable probability that has no atom at this type of sequence. Then, so this means random set of product multi-referendum set of with respect to product probability of u times v. Then, so this means that xy is independent sequence. Then independent selected function selected y again preserves multi-ref normality. So, and Van Barjan also says that the section of random set of product random section of random set is probability 1. So this means that selection function probability of selection function is 1. So so in other words, Van Barjan shows if x is random with respect to uniform measure, then so randomly independent choice of selection function again preserves margin of randomness, but he did not succeed to show the converse direction. Of course, if converse direction is trivial if, for example, y is consists of all 1, then but in this talk I would like to talk about the converse for non-trivial selection functions.
So you say that there is something which Lambalgin's conjectured but not proved, yeah?
Yes, I think that he remarked about some converse, but he did not.
So can you state what he tried to prove but cannot? So just in words, what you say, that it's not very clear written here. What is? There are three, for example, there are several implications, and they don't really understand what is.
So
we want to prove the converse. Yeah.
I think that he shows that x is multi-ref random with respect to uniform measure. Then
we want this to prove that it's
he shows that randomly selected y with random choice of y always preserves margin of randomness. But I think that he tried this direction.
Okay, so he wanted to try to prove that if for every
I don't know. He didn't explicitly write what he wanted to about the converse, but I guess that from his PhD says I guess he tried to show the converse direction of this direction. I think that this direction is non-trivial. So
first line of theorem 2, is that the weaker version of what we generally call?
what?
The first line in theorem 2, like
Correct?
no, theorem 2, the first statement. Is that a weaker version of what we call Van Barjan's theorem? Because it only talks about using y as a selection rule instead of other computations relative to y.
Can you repeat?
I think it doesn't.
So in this talk, I want to study problem of this converse direction, that is from partially observed randomness of subsequence. How do I conclude the randomness of the whole original sequence? So we can solve this type of problem if we restrict some conditions. For example, if there is some computable selection function y such that if P's first statement is P's computable ergodic probability and X is random with respect to this probability, and second statement and X comes from some computable ergodic probability Q, then observed sequence of Y is marginal distribution of P. Then if we restrict X is comes from sequence of some random sequence of with respect to some computable ergodic P, then we can show the equivalence of this statement 1 and statement 2. That is, we can construct a selection function y that that shows the equivalence these two statements. This follows from the if we choose selection function y, then from the partially observed sequence, constructing empirical distribution converges to original probability. So we can show the equivalence of these two types of statements. Then as a corollary, if we choose P to be uniform measure, then we have if X is random, then randomness are recovered from the partially observed sequence if X is known to be comes from some random sequence of computable ergodic process.
Just, can you explain the corollary? So if X is the first part is just X is marginal of random with respect to uniform measure.
Yes.
And what is the second part? Can you explain this?
Second is X is the random sequence with respect to some computable ergodic probability Q. Then, and partially observed sequence is selected sequence is random with respect to uniform measure. So
I don't understand just what are the condition. So for every computable ergodic mu, there exists or some computable ergodic mu. What you are saying? Say it again. The second part.
Sorry, it says
There exists a computable.
Yes.
There
So,
exists a
computable ergodic Q
such that what?
such that
Because I don't understand.
the y is not quantified.
What is
It
y?
is quantified. It's not trivial.
Yeah.
there's a one non-trivial.
What is not trivial?
What is the art?
What is non-trivial solution functions?
Non-trivial means that Y contains infinitely many 0 and 1s. That is non-trivial. No,
Just that it's infinitely many.
so, yeah.
Yeah. So just can you show again statement? Explain it again. So you say that the second condition is that there exists a computable ergodic Q.
Ergodic Q such that
Such as what?
selected subsequence is random with respect to uniform probability.
But this is true because if you just select all of them and select Q and let Q be the uniform, then
But two of one from direction one to two statements is trivial, but the converse is not.
But
From
listen, so what is
direction is not.
RQX/Y belongs? Who belongs to what? I don't understand.
There's this end
there exists in a computable ergodic Q such
Yeah.
that what?
The selected sequence
Q and x over y.
is included.
X is random for Q.
Yeah.
Selected sequence is uniform random numbers. Observed whole the assumption that the whole sequence comes from some computable ergodic probability, but whole sequence is multi-ref random sequence with respect to some ergodic probability, but
No, but I just syntactically don't understand.
Yeah.
X/U belongs to RU, yeah?
Yeah.
The selection of X made by Y should be random. So this is some property of X. But what does RQ mean?
Well,
It's a union over the RQs, and I think there's an and missing between the RQ and the X.
Oh, yeah, that's it.
But RQ is what? Is it
It's the random strings relative to the measured Q.
So X needs to be like
who belongs to this random string?
X.
X.
X is in the union over the RQs.
And there's an and missing on
Up
implication.
that one is normal, but then there's some. I think then there's an and missing and then
A comma.
Right, no.
or
Yeah.
comma just.
Yeah,
Or
comma
really-
missing.
yes.
Put a comma after
Yeah,
right.
yeah.
Oh,
Wait, why is
Right.
this comment?
And well, with and then the y does not affect the first half of the sentence. Yeah, the y could select any second bit, let's say.
Oh, so first you require that X is random with respect to some computable ergodic thing. And second, you require just the one specific subsequence should be random with respect to
No.
uniform. Yeah?
Well, yeah, no,
And what's important that y is not trivial, because it is always true when y selects everything.
Mhm.
I mean, 1 and 2 are trivial equivalent because you can put q
Oh, yeah,
equal
yeah.
to u.
So you separately know that X can be obtained by some computable ergodic method. And also some part is known to be uniformly random. Then the entire thing is uniformly random.
Some proper
Yeah.
part.
Some, non-trivial part is.
but so yes. So but the proof is not so difficult, relatively easy. But we use ergodic theorem to prove this direction. But if we relax this condition for more wide class, that is not. If X comes from just from computable probability, then the problem is much difficult. In the abstract submitted to this conference, I stated some equivalence of this statement, but recently I found some errors in the proof, so I changed theorem to problem. That is, what I want to now studying is this type of showing this type of equivalence, that is, sequence is random, and if sequences comes from some computable probability and observed sequence is random for some non-trivial selection functions, then I want to show the equivalent. I want to construct some non-trivial selection function that proves the equivalence, this type of equivalence.
Say it again. You want to prove that if X is random with respect to some computable measure,
Yeah.
W,
Yeah.
and what?
And if the observed partially subsequence and from the condition of subsequence, randomness of subsequence,
Is uniformly random?
Yes.
With respect to some Y or for every Y or what?
for for some non-trivial,
For some.
yes, yes. For yes. Then
But as I said, selection function should be computable or not.
I think that computability of selection function is not important in this problem. So, of course, I want to study. I want to find some selection function that shows the equivalence of these two statements.
But who depends on W and X?
Why is X once an RU and once an RW? Oh, okay, X is still
But who depends on W and X? I don't understand the syntax.
This depends.
This set depends.
Yes, of course. We admit that the selection function depends on computable probability and sequence X. I think that in the general case, we need selection function that depends on
I
probability.
said, why W with index WX is something you define, or you should you want to construct it solving the problem. I don't understand it. What is YWX?
What?
I am lost.
It
What is
consists-
YWX?
It's a set of selection of set. It's a set of sequences from you use to select subsequences from X.
But it
That's
just-
all it is. It's a
but
set of
it's all-
sequences.
But it's something defined, or it's just a set of all non-trivial selection function, or it's we need to introduce some notion of WY, or it's defined elsewhere. But what is the status of this Y? It's notation for something fixed.
Maybe we should just.
Okay.
So.
I'm lost completely.
So the one point is that, for example, in order to prove this direction, I use convergence of empirical distribution to the true model. But if this assumption does not hold, for example, computable normal number also has a empirical distribution of uniform probability. So if this ergodic assumption is dropped, then this type of approach cannot hold for general case. So anyway, second I also shows a similar analogy for complexity rate notions, such as the rate of complexity is 1. For example, I can show the different type of analogy for Steinhaus theorem, such as if selection function satisfies this, complexity rate is 0 and density positive, and also we can choose for sufficiently large density. Then ratio is 1, complexity ratio is 1, converges to 1, and equivalent to subsequence complexity ratio of subsequence 1 for such selection functions is equivalent. We can choose this type of selection function as a random sequence of some type of computable probability. This, for example, we can
again, it's for some Y or for all Y in a random. You say for Y belongs to RW.
Yeah.
But what does it mean? For all Y or for some Y?
All. For all. Statement 2 shows that this holds for all selection function Y.
But if Y is equal to X, then we get only
No. Double satisfies these conditions. Yeah.
Oh.
So we can choose selection function as roughly speaking to zero entropy sequence. We can choose, for example, we can make such computable double from irrational rotation of parameter row, and then this is a zero entropy sequence, and with a mixture of them, then this satisfies these conditions. So I have no time, but so I also, there is also algorithmic analogy for Kamai-Wise theorem. That Kamai-Wise theorem shows that for example, sequences generally do not have empirical distributions. So relative frequency do not always converge, but we can consider the cluster point of relative frequency. So the cluster point of empirical distribution is defined by the if the relative frequency is convergence for subsequence, then cluster point of empirical distribution defined by this way, and we can show that this is not empty. So, and the pointwise entropy of sequence is defined by this way. Then, and Kamai shows the necessary and sufficient condition that the selection function always preserves normality is the entropy of the sequence is 0. Van Lambertian conjectures algorithmic analogy for this Kamai-Wise theorem, such as this type of. He conjectures equivalence for these two statements, but I show some different analogy. For example, if this two statement is equivalent for y is computable and the randomness and sequence is random, and this these two type of statement equivalent means that y is computable and x is selected function, selected sequence is always random with respect to random sequence relative to y. These two statement equivalent. Also, for complexity rate notion, we have this type of equivalence, that is the complexity of selection function of entropy of complexity entropy of selection function of is 0, equivalent to the, it always preserves the complexity ratio normal complexity ratio. So I think that from these two observations, I think that it does not negate the Lambertian's conjecture, but I think that I doubt that the original conjecture is not true. So, thank you very much.
All right, I think we might have time for one very quick question, but otherwise perhaps hold questions for lunch. In that case, let's thank our speaker again.